Hello friends, welcome to the next segment of polymer testing. In this particular segment, we are going to discuss about the mechanical properties, especially hardness, tensile and compression. Now in the previous lecture, we have covered the measurement of the rheological properties. We described about the classification scheme of rheometers and discussed about the rotational rheometer, capillary rheometer, extensional rheometers. In this particular segment, we are going to cover about the mechanical properties, especially pertaining to the hardness, tensile, compression, all these things we are going to cover in this particular aspect. Let us talk about the hardness. The term hardness is typically understood to refer to a measure of modulus derived from the material's resistance to indentation, although it has also been used to refer the resilience and scratch resistance. So, hardness is not a fundamental characteristic and the mechanism of deformation caused by an indenter is a combination of tension, shear and compression. The shape of indenter, the depth of the indentation and the length of a time between the indentation and the measurement all affect the outcome. The hardness is usually or always included in the characteristics of rubbers and frequently applied to the metals. It has been used as to plastic less frequently. The indenting force can be applied in different ways and especially in three ways. One is the application of a constant force followed by the measurement of the resulting indentation. The force needed to create a consistent indentation which is measured, and the use of spring causes the indenting force to vary with the depth of the indentation. There are several different indenter geometries utilized, including ball, truncated cone and a pyramid. The ball is preferred for rubber and may be applied to relatively soft materials, but the pyramid form is derived from the technique developed for metals and frequently applied to stiff plastics. A truncated cone is employed in the durometer that is more frequently used. In testing of metals, the indentation is often measured after a indenting force has been removed, and whereas the testing of rubber, the force is always applied. Now let us talk about the standard methods. The shore durometer. The shore durometer or hardness scale, specifically the shore A and shore D, is likely to the most widely used scale, and these durometers are compact handheld devices having the indenter that press into the surface of the material being measured while being supported by the springs of a specific stiffness. A suitable scale marked in hardness degrees is used to measure the indenter's penetration depth, and the scale usually traditionally dial gauge with a digital readout. Now here you see the different type of shore indenters. Let us talk about the shore A test, usually described by the ISO 868. Both the typical shore version, they are standardized. The shore A scale is applied to a soft plastic as depicted in this particular figure. The indenter in this technique is truncated cone with a flat bottom and included angle of 35 degree that operates under the spring pressure. This is given by F is equal to 550 plus 75 HA, where F is applied force in millinewton and HA is the hardness. Let us talk about the shore D scale. This is suitable for the typical harder plastics material. Now it functions with the spring provided by and has a sharper indenter include with an angle of say 30 degree with only a very tiny radius 0.1 mm tip, this one. Now this is represented by F is equal to 445 HD, where F is the applied force in millinewton and HD is the hardness. Now over the normal operating range, the shore A scale is virtually similar to the IRD HD scale given by ISO 48. The test piece for both durometers must be at least 6 mm thick and measurement must be taken at a minimum distance of 12 mm of any edge. So the amount of time the load is applied before a reading is obtained is very crucial, since the measured hardness diminishes over time. The best way to calibrate durometer is to measure the spring force at various deflections. An imperfect approach is described in the standard 868 of ISO. For both plastic and rubber, specific calibration techniques are now being developed. Theoretically, only one calibration standard is required to cover both the materials. Let's talk about the ball indentation. The test piece should ideally be 4 mm thick, and the only restriction is that the test piece underside shouldn't exhibit any deformation after testing. So, under a specific load, a hardened steel ball with a diameter of 5 mm is driven into the test surface, and the indentation indicating device is initially adjusted to 0 and a load of 9.8 Newton is applied to the surface. The next step is to apply the major load, which is selected from a list so that the resulting indentation ranges between 0.15 to 0.35 millimeter, and usually load is applied for 30 seconds in toto, and the area of impression and the ball indentation hardness are connected and expressed in Newton meter over meter square. This must be 10 valid test with the indentation within the required range, and but this instruction is not provided. Thus, it must be assumed that the tests are average. Rockwell test. This employs a hardened steel ball as the indenter, although the 4 different diameter corresponding to the R, L, M and E Rockwell scales are specified. Now, here the scales being employed affect both the minor and a major burdens. Now, in this particular table, you see the various scales of Rockwell harden. Now, here the Rockwell scales R, L, M and E, and you applied the minor load and then the major load, and you are having a reference of indenter dia in millimeter. So, this by this way you can see the effect of all those Rockwell scales. Now, for all scales, the required test piece has minimum thickness of 6 mm and the indentation gauge is reset to 0 after applying the minimal load. The main stress is applied within 10 seconds, withdrawn after 15 seconds. In contrast to the previous processes, the indentation is measured after the load has been removed. The fairly odd formula, this one, where E is the depth of impression upon removal. Fairly odd formula, this is represented by this one 130 minus E, where E is the depth of impression upon removal of primary load in units of 0.002 mm is used to calculate the Rockwell hardness number. Now, the hardness should fall somewhere between 50 and 115 on the scale, and the average of 5 reading should be calculated. The Rockwell alpha. This method, the indentation is measured while a load is being applied, and the correction identical to that the ball indentation method is then applied. So, the inaccuracy due to the machine stiffness will rise with load. So, only R scale is thought to be appropriate one apart from given 4 scales, and in this instance 150 minus D is the formula where D is the corrected indentation yields the Rockwell alpha hardness number. So, the Rockwell alpha RA and the ball indentation hardness H, they are connected by this particular mathematical representation, that is H is equal to 448.6 to the power 1.23 over 150 minus R alpha. Let us talk about the softness. The standard softness measurement of for flexible polymer is provided in the British standard 2782 method 365A. Although the results are essentially the same as those of the rubber hardness test, they are expressed substantially differently. The softness number is reported as the indentation in units of 0.01 mm rather than being converted to hardness degrees. For the standard test to be valid, the test piece must be between 8 and 10 mm thick, and no measurement should be taken closer to 10 mm for any age. Special instructions they are provided in the standard plasticized polyvinyl chloride, which is known to change in hardness over time after molding and to produce a different result depending on whether compression or injection mold test pieces were employed. Now, it is necessary to measure the softness in order to reduce the time effect. Let's talk about the Barcol hardness. A portable hardness meter, often known as a durometer, is the Barcol impressor. The Barcol model 934-1 is used in the procedure specified in EN 59, which is specialized for the glass reinforced polymers. The indenter is truncated cone method of hardness steel with a flat tip of say 0.137 mm and angle of 26 degrees. So, under the undefined spring pressure, it is pressed against the test piece with the maximum indentation being measured in the units of 0.0076 mm. The Vickers hardness, the Vickers method makes use of a right diamond pyramid on a square base as the indenter and measures the mean diagonal of the impression with this expression. Now, here the expression is HV is equal to 2f sin theta by 2 over d square, where HV is the Vickers hardness, this is hardness, F is the applied load in kilogram, D is the mean diagonal width of the impression mm, and theta is the apex angle of the pyramid, let us say 136 degree. So, the diagonal measurement is rather simple in plastics because the pyramid indenter typically leaves a crisp impression, but the measurement is only taken after the elastic recovery. Now, Brinell hardness. Unlike Rockwell, the Brinell hardness method measures the diameter of indentation rather than using a ball indenter. Now, with plastic, this typically not very satisfactory and is far less common than Vickers or Rockwell. And the Brinell method is standardized used to with the use of metal in ISO 6506. Now, the hardness relationship, being given by the expression HB is equal to 2F over pi d square 1 minus d over d square to the power half. This HB is the Brinell hardness, F is the applied load, D is the diameter of the indenter, which is usually represented in mm, and d, small d is the diameter of the impression made, again it is in mm. Now, tensile stress strain, the force necessary to pull the material apart and the displacement that the material experience as a result of the applied force are both measured to determine the tensile stress strain properties of the material. Now, material scientists, the technicians, the specifiers of the material and designer, they can get inside into the material's prospective performance by being aware of these properties. Let us talk about the stress. It is usually important to introduce a number of definitions in order to translate the force and displacement into stress strain characteristics. So, the stress usually represented in megapascal is equal to force over area in mm square. Now, if a rectangular bar like this of a cross sectional area AB in square millimeter and applied force is say F acting upon, then the tensile stress in the bar is simply F over AB. Now, it should be emphasized that the stress often measured in tensile tests is based on the material's original dimensions before the application of any force, and then that is known as the engineering stress in general. Now, as a bar is stretched in cross-sectional area would compress, causing a higher real stress in the material than would be predicted by an engineering stress estimate, so called the true stress, and it can therefore be computed if the cross-sectional area of the material subject to the applied force is observed and the stress calculation is based on the measured dimension. Now, here you see that strain, this is the extension over the original length. So, this is the prior to the force application, and if you apply the force then it is stretched. So, this is the rectangular bar of length L prior to the application of a load, say L naught, and the length L1 of the bar after the application of the force. So, then the extension of in delta L of the bar is simply L1, this one is L1 minus L naught, and therefore, the strain induced in the bar is L1 minus L naught over L naught. Now, examining the stress strain characteristics of a solid with perfect elastic behavior all the way to brittle failure, it can be seen in the relationship between the stress and strain, which is linear up to the failure point, and as a consequence of the relationship, stress over strain is equal to constant and is known as the elastic modulus of the material. So, the modulus is equal to stress over strain. Now, this particular figure shows the typical stress versus strain characteristics for a perfectly elastic solid, and this you can see the failure point. Now, there are 4 basic generic categories of stress strain properties of polymeric material. One is the tough material with the yield stress greater than the failure stress, and numerous characteristic values connected with the test substance can be identified, and tensile yield stress, the lowest stress at which the strain increases without causing stress to increase in turn, and the tensile stress at break, that is called the failure stress. Now, the tensile strength of the material at failure. This particular plot shows the idealized stress strain relationship for a typical tough plastic material with a yield stress greater than the failure stress. Another is the tensile strain at yield, that is the yield strain. The material's corresponding tensile strain in the yield stress. Now, tensile strain at the break failure, this is the material's corresponding tensile strain in the failure stage. This particular graph again shows the typical plastic material that yield stress greater than the failure stress. Another type is the tough material with the yield stress lower than the failure stress. So, after reaching a yield point, some material once more start to display a rise in the stress with increasing strain. So, the characteristic value for this material, like the tensile yield stress or yield stress, this is the lowest stress at which the strain rises without an equal rise in stress. The tensile stress at break, that is the failure stress. The tensile strength of the material at failure and tensile strain at yield, or sometimes referred as a yield strain, the material's corresponding tensile strain at the yield stress. Then tensile strain at break, that is failure strain, the material's corresponding tensile strain at the failure stress. Now, tough material with the same yield and the failure stress, the material that does not display the brittle failure does not show a decrease in the stress at yield point. Now, this is the figure, this is the typical non-linear stress versus strain characteristics of a tough thermoplastic showing no drop in stress at yield. Let us talk about the test method and the standard methods. The rigid cellular material or sandwich structure comprising cellular material not covered by the ISO standard 527 requirement for the tensile testing of the plastic material. For general purpose ASTM standards being used, only the test piece configuration and test speed differ between these two standards. Now, there are various terms to be defined in the tensile testing. One is the gauge length, the initial distance between the gauge mark on the central part of the test specimen. Then speed of testing, the rate at which the testing machine's grip separate during the test. Then tensile stress in the original cross section's tensile force per unit area inside the gauge length, and that is being carried by the specimen at any particular time. Then the tensile stress at yield, that is a yield stress, the initial stress level at which the strain increases without a corresponding increase in tension. And tensile stress at break, the tensile stress at which the test specimen ruptures, that is break. Then tensile strength, the maximum tensile stress sustained by the test specimen during the tensile test. Then tensile stress at percentage x% strain, the stress at which the strain reaches the specified value of x expressed as a percentage. Then tensile strain, the increase in the length per unit of original length of gauge. Then tensile strain at yield, this is the tensile strain at the yield stress. Then tensile strain at break, the tensile strain at the tensile stress break if it breaks without yielding. Then tensile strain at tensile strength, the tensile strain at the point corresponding to the tensile strength if this occurs without or at yielding. The normal tensile strain, the increase in the length per unit original length of the distance between the grip or grip separation. The nominal tensile strain at break, the nominal tensile strain at the tensile stress at break if the specimen breaks after yielding. Another definition is the nominal tensile strain at the tensile strength if the specimen breaks after yielding the nominal tensile strain at the tensile strength. Young's modulus or the modulus of elasticity in tension, the proportion of a stress differential to a strain difference, and the guideline specifies that these strain must be between 0.05 and 0.25. This is called the Young's modulus as well. The term film does not fit to this particular definition. The Poisson's ratio, the initial linear section of the longitudinal versus normal strain curve, and that has a negative ratio between the corresponding strain in the direction of pull and the tensile strain in one of the two axes normal to the direction of pull. Now, this is the typical schematic diagram of electromechanical twin screw tensile test machine under the head of this tensile testing machine. The commercial tensile testing devices come into two varieties. One is the electromechanical and second one is the servo hydraulic. The electromechanical devices come in two variation, central screw with the twin screw, the most prevalent type in the twin screw. Now, this is the servo hydraulic tensile testing machine, where the hydraulic cylinder, ram, load cells, all these things are there. The servo hydraulic machine do not use the moving crossheads. They applied the tensile or compressive force through a hydraulic ram. Now, grips. The grip system is set up so that the test specimen's main axis and pull direction through the grip assembly's center line coincide. The grip must prevent the test specimen from the slipping in relation to them and must maintain or increase pressure on the test specimen as the force being applied to it rises. The grip system must not result in early grip failure. This is the typical wedge grip assembly, where you see that these are the wedge grips and you can put the specimen over here. The extensometer. The extensometer should measure the change in the gauge length with an accuracy of say 1% of the pertinent value or greater. There are numerous varieties of extensometer with only differences being the gauge length and the greatest elongation they will measure. In each case, the accuracy is plus minus 2%. So, the degree of elongation being measured, like the grips, determines the level of accuracy needed in length units. And there are many different type of extensometer that can be used to monitor the strain in the tensile test. One is the clip-on strain gauge type for the high modulus material, and another one is the non-contacting type of extensometer for the low modulus and or thin material. These may be the optical laser and the video type, like where the specimen would be severely distorted before the application of a test load due to the weight of a clip on the extensometer. Now here you see the different type of extensometer, like this is the optical extensometer. You see that the gauge, and this is the core of this particular extensometer, where the laser transmitter or receivers are there, and there are the light beams and light sources and the photoelectric sensing devices, they are equipped. This is the laser extensometer. Here you see that different type of laser transmitting devices and laser beams, and this is the video extensometer. This is equipped with a video camera which is connected with the computer to record all kind of the deviation in your data. Now let us talk about the test piece geometry. The two-dimensional dumbbell form or the flat strips serve as the test pieces. Sometimes the ring test pieces are also used for rubbers and 3D dumbbells for the certain type of plastics. The fundamental property of dumbbell is that they are method of concentrating loads so that the failure occurs in a narrow area and not primarily where the test piece is held. So dumbbell come in a variety of sizes and have a different detailed shapes depending on the standards, and they are actually the outcome of a theoretical hypothesis or actual studies with the goal of maximizing stress dispersion. So as per the ISO standard 527, there must be a minimum 5 test pieces for each direction must be evaluated, and separate sets of test pieces are necessary if modulus and ultimate strength tests are conducted at different speeds. So as per this, according to the material being tested, these standards specify the shape and the size of pieces. And there are numerous test specimen type that can be used with certain standards like ISO 5272 standard test conditions for molding and extrusion plastics. Like here you see this is dumbbell type of the test species, and different types, type 1A and type 1B, this is given, and this is the type 1BA and type 1B. So all different type of the things test specimen has been given. Here again this another type of type 5A and type 5B. So here this is the test specimen of type of 5A and B. Another ISO 527-3 test conditions, they are used for the plastic films and sheets. Now less than 1 mm thick type 2 test specimen, they are desired, although the cellular materials and the plastic reinforced with textile fibers are not thought to be acceptable for this type of test under the given conditions. So for rigid sheets there are different type of a test, like here this is the shape of the test specimen, and different type of a test and specimens are given, like this is recommended for the film and sheets with a very high strain at breadth. The ISO 527 part 4 and 5 test conditions of fiber reinforced plastic, because the fiber reinforced plastic play a very vital role in the commodity system. So their test must be specified, like another test 527 for 4, this covers the isotropic and orthotropic materials. Another test deals with the unidirectional materials, and usually the parallel strip test pieces are used with the tab ends adhere to the strip to add gripping. Now when we talk about the procedures, so ISO 527 standards specify the overall tensile resting procedure. The temperature and the air conditioning, they are not specifically advised, and it is important to avoid the pre-stresses and to ensure that the test piece is properly aligned with the machine's axis, and especially when using less stiff materials. And as per this third standard, the specimen should not support the weight of the extensometer while evaluating the thin sheets or film material. With the exception of modulus, the test speed should be chosen so that it produces a strain rate of say 1% of the strain rate per minute, and it is recommended that it be chosen accordance with the relevant material specification. And the film and sheets, they are often tested at 550, 100, 200, 300 and 500 mm per minute as per the ISO 527-3 standards. The force elongation curve is typically automatically recorded, and the precise characterization of the Young's modulus between the two arbitrary strain level 0.05% to 0.025 percent of gauge length necessitates extremely high extensometer accuracy and is likely impossible in many situations. The Poisson's ratio can be measured, although this is not recommended or not common and necessitates a way to precisely record the change in the test piece width or thickness in addition to the elongation measurement. Let us talk about the compression. The compression strain, stress strain properties of the material should be used in mode of deformation of soft material like foam, rubber, stiff plastics, all those things. On test pieces that have a height that is noticeably smaller than the compressed area and often a disc or short cylinder standard compression test on rubbers and foam they are conducted. The ratio of height to area is then very important. So, a test piece may be compressed in one or two circumstances. One is the perfect slippage exists between the test component and apparatus and compressing part without any slipping at all. The test pieces such as a rigid prism, cylinder or a tube with height greater than the diameter or width, they are frequently used in the standard test procedure for rigid plastic. The compression test may also be performed using the universal testing machines, and the compression load cell is a part of that particular device, and the compression is done between the two parallel steel plates. Ones involving the compression typically create a lot more force than ones involving the tension. And the compression platens are moved using the suitable transducers in order to measure the strain. If the machine is sufficiently rigid in relation to the test piece or to prevent the introduction of fault, machine crossheads movement may be used. The measurement of plastics compressive characteristics, this usually addressed in the ISO 604 standard. The test piece for the compression testing must have very flat end faces and they are parallel to the test piece along axis to a tolerance of 0.025 mm. For their preparation, lathes or milling machines they are advised. In compression test, buckling is a crucial factor, and compared to the tall, slender pieces, short squat test pieces are far less likely to buckle. Therefore, there are some limitation on the ratio of the important dimension. Now, the length of the test piece and the direction of the compressive force being applied and the critical dimension perpendicular to these two important dimensions. Now, usually when we talk about the two key dimensions are the test piece alongside of the direction being important, and the parameter govern the buckling is given as epsilon c is less than equal to 0.4 x over L to the power 2, where this epsilon c is the maximum nominal compressive strain experience during the test, and L is the length of test piece and x is the diameter if the test piece is a cylinder, the outer diameter if it is a tube, or the thickness, and that is a smaller lateral dimension if it is a prism. Now, x over L ratio is not less than 0.8. Usually it is recommended for measuring the modulus and other test which is not less than 0.4. So, the two preferred test pieces sizes they are given. For modulus length equal to 50, the width may be 10 mm and the thickness 4 mm, and for strength length 10 mm with 10 mm and thickness 4 mm. If an optical approach is employed to measure the change in length, the gauge marking they are necessary to measure the compressive modulus. So, the option for the speed are 1, 2, 5, 10, 20 mm per minute, and the speed of modulus should be close as possible in values of to 5% of the specimen length. For brittle material, the speed of instant testing should be close to 10% of the specimen length, while the ductile material it should be closest to 50% of this length. So, dear friends, this comes to the end of this testing segment, and we discussed all aspects which are relevant for the polymer testing, And for your convenience, we have enlisted several references which can be utilized if needed. Thank you very much.